Right. Okay. Good morning, all. We'll start. So, can you confirm whether my audio is clear and about the video quality? Okay. Right. Okay. We'll start. Right. So, as we have planned today, we'll be starting the new lesson, center of gravity. So, in the last month, we have completed equilibrium of forces, right? Vectors, equilibrium of forces, vectors and equilibrium of forces. And this month, according to this month plan, today we are starting center of gravity, and after finishing center of gravity, during the month we will be completing friction as well. So these two are the two main lessons to be covered in the class during the month of February, right? First one, this one today we are starting today, center of gravity, right? And then friction, right? These two are the two main lessons to be covered in the revision class during this month, right? So when it comes to center of gravity is a like maximum two-day thing, right? Maximum 2-day thing. Today we are starting, and we are going to finish off everything in center of gravity by next week, right? And when it comes to friction also, we'll be finishing all the things in friction roughly within 2 days, right? So that's what the monthly plan is. And after friction next month, we'll be starting rotational motion and circular motion, like main parts, critical parts in our syllabus, right? And in the reverse class, right? This is what is ongoing on this forward class, this revision class, right? And these lessons are to be covered in the reverse class, right? First one, elasticity. And next, we are to start matter and radiation. Right? These two are going on the reverse class, right? Second. Right. So these are the lessons to be covered. For revision students here during this month of February, right? So you can cover these things. This is for 10 marks, 10% of marks, right? This elasticity with Ragname, I mean all properties of matter, since we have covered surface tension and viscosity already, right? This is a 10% lesson, and this is also a 10% lesson, matter and radiation, right? So here we are in the mechanics part. All together for mechanics, you have 20 marks, 20% of marks, right? Okay, then we'll jump into the discussion. As a heading, put down center of gravity. As a heading, write down center of gravity. Center of gravity. Center of gravity. Center of gravity. Right. So, any thoughts what center of gravity is? Any thoughts what center of gravity is? Right. Before I straight away jumping into the discussion, any thoughts what center of gravity is? Listen. Now, if we consider any type of an object, right? If we consider any type of an object, right? Any type of an object, right? We know any object has a mass, no? Any object has a mass. If the object has a mass, it has a weight. If the object has a mass, it has a weight, right? Then, if weight is a force, weight is a force, no? Since weight is a force, it should have an acting point and an acting line. Since weight is a force, it should have an acting point and an acting line. Two things, acting point and acting line. Acting point and acting line, right? The acting point of weight of the object is called center of gravity. Now, as an example, if this weight acts from here, say this weight acts from here on this object, this point, from this point, that particular point is called center of gravity. That particular point is called center of gravity, right? So simply, center of gravity is the point where weight of an object acts, right? Weight of an object acts. For any type of an object, right? Since it has a mass, it has a weight, so therefore it has a center of gravity, right? For any type of an object, it has a center of gravity. And sometimes center of gravity is located inside the body, inside the object, and sometimes outside the body as well. Now, as an example, if we consider this type of an object, something like this, right? If we consider this type of an object, something like this, center of gravity can be somewhere outside the body as well. It can be somewhere outside the body as well. And sometimes it can be biased to some direction as well. Biased to one direction, biased to some direction, right? It is not always symmetric. Not always symmetric. Symmetric cases are there, but not always. Not always. Not always. Right? Now, in these kind of a case, something like this. Something like this. Center of gravity will be somewhere towards this side. Something like this. Right? So therefore, before starting our discussion, the first idea you have to have is center of gravity is the point where weight of the object acts. And it can be a point either inside the body or outside the body as well. Simply, it can be any point in the space. It can be any point in the space. Right? Got it? So before writing this down, before taking this down, write down first, write down the point where, write down the point where, the point where the point where the point where weight of an object, the point where weight of an object, the point where weight of an object acts, the point where weight of an object acts, the point where weight of an object acts is called center of gravity. The point where weight of an object acts is called center of gravity. Is called center of gravity. The point where weight of an object acts is called center of gravity. Right? As a next point, write down with a red pen. As a next point, write down this with a red pen. Center of gravity of an object can be, center of gravity of an object can be, center of gravity of an object can be, center of gravity of an object can be at any point on the space, at any point on the space, can be at any point on the space, can be at any point on the space, within brackets, inside or outside the object, inside or outside of the object. within brackets inside O, outside of the object. Inside O, outside of the object. Okay. Now take this down. Take down few examples. Few examples. Right? These are few examples. Take it down. Right? Right? Okay, write down next. Write down next as a heading. As a heading. Equilibrium of an object. Write down. Equilibrium of an object. Equilibrium. Equilibrium of an object. Equilibrium of an object. With center of gravity. Equilibrium of an object 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 with center of gravity, right? Look at here. Right. The surface which is in contact with another mutual surface of an object, right? The surface which is in contact with another mutual surface, right, of the object. Now here this one is called the supporter. Is called supporter, right? We call it supporter. This is called the supporter. Supporter, right? Now, in terms of center of gravity, this is how this happens. If center of gravity of the object and acting line of weight is inside supporter, right? Is inside supporter, inside supporter, that is called a stable equilibrium because that is not going to fall. That is not going to fall, right? That is called a stable equilibrium. This is called a stable equilibrium, right? And something like this. See, if center of gravity of the object, if center of gravity of the object, now this is the supporter surface again, this is the supporter surface, surface in contact, right? If center of gravity of the object is at the very end of the supporter like this, right? Center of gravity and acting line of weight. At the very end, that is called a neutral equilibrium. That is called neutral. That is called neutral, right? And if the center of gravity is, outside the supporter like this, if the center of gravity is, if the center of gravity is outside the supporter like this. Now this is the supporter surface. Still this is the supporter surface, right? And if the center of gravity is outside the supporter, right? This system is not going to retain. This is not going to sustain, right? Definitely the system is topples, right? It collapses, it falls, right? Therefore, it is called an unstable equilibrium. So with respect to the position, location of center of gravity, that is how the equilibrium changes. Now, as an example, let me show you an example using here, this demonstration. Look at here. Right. Look at here. This one. Using this, if I explain, right? If I explain using this, now when we are keeping this like this, the supporter surface is this whole area here. The supporter surface is this whole area here. Likewise, right? Now, since this object is a symmetric object, center of gravity is somewhere around the center, right? Since the object is a symmetric object, center of gravity is somewhere around the center, right? Keep that in mind for a moment. Then for sure I know that center of gravity is somewhere here. Now, if I keep this like this, right? Contacting surface is that area. Contacting surface is that area. Then there is a supporter surface. That is a border, right? And now center of gravity is inside the border. Center of gravity is inside the border. If there is inside the border, this equilibrium is stable. This is not going to fall or change its state of equilibrium. That is stable. That is stable. It will stay as it is, right? Until we make a change, it will stay as it is, right? And now, if I make some space here like this, see, by taking this to this side, at some point here, see, now still this is in equilibrium. Still this is in equilibrium. Now the supporter surface is from here to here. Supporter surface is only from here to here, right? But still this is an equilibrium. This is an equilibrium, right? Because center of gravity is at the edge of the supporter, where the object is at neutral equilibrium. The reason to say this as neutral is, right, the very next point after neutral equilibrium is unstable. And if the center of gravity moves to the other side, that becomes stable, right? So neutral equilibrium is exactly in between unstable and stable equilibriums. That's why this is called neutral. This is called neutral. Now, if I give a displacement to this side, see, it becomes stable. If I give a displacement from this neutral equilibrium to that side, see, it falls because it becomes unstable, right? So unstable equilibrium means something like this. If the center of gravity is away from the supporter surface, this is going to fall, right? We can't stop this. This is going to fall. So therefore, the idea is if you need to keep an object in equilibrium, either it should be at a stable equilibrium like this, or it should be at neutral equilibrium at least like this. Neutral equilibrium at least, right? So therefore, last point, the object can be in equilibrium is neutral equilibrium. The very last point the object can be in equilibrium is the neutral point, right? Very last point the object can be in equilibrium is the neutral point, right? In the unstable equilibrium, even though we say this as unstable equilibrium is not an equilibrium, right? The object is unstable. The object is going to fall. It is going to topple, or it is going to collapse from the system, right? Take it down. Stable equilibrium. Stable equilibrium. Neutral equilibrium. Unstable equilibrium. And we'll be writing a note under each diagram. So keep some space below each diagram to write the note. Keep some space below each diagram to write the note. Right? There are two things we look at here. One is the center of gravity, and the other one is actin line of center of gravity. There are two things. If center of gravity or actin line of center of gravity, sorry, actin line of weight, actin line of weight inside the border, that is stable, something like that. Center of gravity and actin line of weight is at the edge of the border, right? We will be writing the note under each scenario. Okay, write down below the first one, first diagram. Write down below the first diagram, right? Like this. You can asterisk mark. Write down below the first diagram. Write down. If center of gravity, below first one, if center of gravity, if center of gravity, if center of gravity slash slash actin line of weight, if center of gravity slash actin line of weight, if center of gravity slash actin line of weight if center of gravity slash actin line of weight is inside suborder, 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 it is called, it is called, it is called a stable equilibrium. 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 Right, neutral equilibrium. Under neutral, write down. Under neutral, write down. If center of gravity, if center of gravity, if center of gravity slash actin line of weight, if center of gravity slash actin line of weight, actin line of weight is at the end of suborder, is at the end of suborder. 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 It is called a neutral equilibrium. It is called a neutral equilibrium. It is called a neutral equilibrium. Right? Under unstable, write down if center of gravity, if center of gravity, slash, if center of gravity slash actin line of weight, if center of gravity slash actin line of weight, if center of gravity slash actin line of weight is outside suborder, is outside suborder, is outside suborder, it is called an unstable equilibrium. It is called an unstable, it is called an unstable equilibrium. It is called an unstable equilibrium. Okay, then tell me, what are the two equilibriums out of those of which or where the object can be kept in equilibrium? That is only stable and neutral, right? That is only stable and neutral. If the object is unstable, which means there is not an equilibrium, even though we say there is an unstable equilibrium, there is not an equilibrium, the object will definitely fall. The object will definitely fall, right? So, in other words, the object will definitely topple. The object will definitely topple, right? So, we'll take that learning from this. Write down below with a red pen. Write down below with a red pen. Now, this is a common point. As a common point, write down below with a red pen, put an asterisk mark, and write down. In order to keep an object in equilibrium, 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 without collapsing, without collapsing slash falling, without collapsing slash falling, without collapsing slash falling, its center of gravity, its center of gravity, its center of gravity, its center of gravity should be located, its center of gravity should be located, its center of gravity should be located inside the suborder, its center of gravity should be located inside the suborder, its center of gravity should be located inside the suborder, its center of gravity should be located inside the suborder, inside the suborder, right? Underline, no highlight, inside the suborder, 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 right? Underline, no highlight, inside the border, right? Listen. Now, the opposite of this is, right? If an object is going to be falling, if an object is going to be falling, going to fall, going to fall, going to topple, right? The requirement to be satisfied is its center of gravity should be outside the border, right? Now, as I showed you before, if this is going to fall, see, once the center of gravity is outside the border, only it is falling. Right, next point, keep using red. Next point, keep using red. The requirement to be satisfied, the requirement to be satisfied, the requirement to be satisfied, the requirement to be satisfied to fold an object, to fold an object, to fold an object is its center of gravity being 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 outside the supporter, is its center of gravity being outside the supporter, outside the supporter, outside the supporter. Right, next point, keep using red. These are the most important, these are going to be the most important points when it comes to our questions coming up. Right, next point, the minimum condition, the minimum condition, the minimum condition, the minimum condition under which, the minimum condition under which, the minimum condition under which, the minimum condition under which the object is, the minimum condition under which the object is, the minimum condition under which the object is in equilibrium, the object is in equilibrium, the object is in equilibrium is center of gravity being, 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 is center of gravity being at the end of supporter, at the end of supporter, is center of gravity being at the end of supporter, at the end of supporter, within brackets, neutral equilibrium, within brackets, neutral equilibrium, neutral equilibrium, right? Neutral equilibrium. Right. Listen. So first, we are going to find the center of gravities of some objects. So before that, we'll be using force dividing ratios, something called force dividing ratios, to solve this, to solve center of gravities, right? So for that, let's see how force dividing ratios are proved, and then we are going to use that result as a proved result when finding center of gravities, right? As an excellent, write down force dividing ratios, force dividing ratios. And under that, write down principle of force moments. Write down principle of force moments. Principle of force moments. Principle of force moments. Principle of force moments. Okay, write down this with a red pen. Write down this with a red pen. Put an asterisk mark and write down the principle with a red pen. Write down the principle with a red pen. Write down. Write down algebraic summation of force moments, algebraic summation of force moments, algebraic summation of force moments by each force, algebraic summation of force moments by each force, algebraic summation of force moments by each force about a certain point, about a certain point slash axis, about a certain point slash axis, about a certain point slash axis is equal to the force moment is equal to the force moment is equal to the force moment due to resultant force is equal to the force moment due to resultant force about the same point, about the same point slash axis, 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 right? About the same point slash axis. Okay, now listen, look at the board. Let's say these two forces, let's say these two forces F1 and F2, right? Accept these 2 points. Say these points are A and B. Say these points are A and B, right? And let's assume this total separation as L. Let's assume this total separation as L, right? From vectors we know, if we are to think of the resultant of two parallel vectors like this, resultant of two parallel vectors is always in between. Resultant of two parallel vectors is always in between, and it is closer to heavier force. That is closer to heavier force. Now we don't know which force is heavier, that we don't know, right? But for sure we can say this resultant is going to be in between. No? This resultant is going to be in between. And the value of the resultant is, since there are two parallel forces, right? Two parallel forces. We know if we have 2 newtons acting rightwards and 3 newtons acting rightwards, the resultant is going to be 5 newtons acting rightwards. Parallel forces. Then resultant of these two can be written as F1 plus F2. Resultant of these two can be written as F1 plus F2. Right? And the point where resultant acts on the system, let's assume it as G. Right. Now, a small task. Listen carefully. A small task. First copy down this diagram, and then after copying down the diagram, try to apply the principle of force moments, right? That is what I just gave, right? That is what I just gave above. Apply the principle of force moments, and I need you to find two things. One is the length AG and then the length BG. Try to find these two. And you should get an answer in terms of F1, F2 and L only. you should get an answer in terms of F1, F2, and L only. Right. Give it a try. Give it a try. Give it a try. Right. Send your answers if you got anything. Send your answers if you got anything. Any answers? Any answers? Any answers? Right, okay, see, time is enough. Right, time is enough. Now, if you apply force dividing ratios, you may apply the principle of force moments. See, using principle of force moments, we can argue like this. If I write force moment about A, using principle of force moments, using principle of force moments, right? Using principle of force moments. Now, if I write the force moment, about A, right? So what it says is force moment by the resultant is equal to, right, algebraic summation of force moments by other forces. Then force moment by the resultant can be written as, if this distance is AG, resultant is F1 plus F2, no? Then force moment by the resultant is F1 plus F2 times AG, right? F1 plus F2 times AG. F1 plus F2 times AG, right? And if you are writing force moments about A, F1 is not contributing. F1 goes through point A, it is not contributing. So only F2 comes. Distance to F2 is AB. AB is given as L, right? And only F2 comes, right? By F1 there is no force moment. Only F2 comes. F2 into AB, right? Now this is F1 plus F2 times AG equals F2 times L. AB is L, right? We wanted AG, so AG is L over F1 plus F2 into F2. L over F1 plus F2 into F2, right? AG is here. AG is here. Similarly, we can find BG as well. Similarly, you can find BG as well. Same thing. Similarly, you can find BG. Find BG. To find BG, what if we consider the force moments about B? Force moments about B, right? About B by the resultant, that is F1 plus F2. Resultant is F1 plus F2. Distance is BG. And F2 is not contributing as it is going through point B, but F1 comes. Distance to F1 is AB, right? So this is F1 plus F2. BG equals F1, AB is L. See, BG comes as L over F1 plus F2 into F1. Right. So likewise, we can prove two answers for AG and BG. Likewise, we can prove two answers for AG and BG. Right. First, take it down. Take it down. Right. Right. Is it clear? Now we are going to use this proved result as an equation to carry forward. See, now this is how we are going to use this. Say we have two forces which are acting at a separation L like this, and say these two forces are P and Q, points are A and B, and their resultant is for sure going to be in between, right? And the value of the resultant is P plus Q, right? Let's say that point is G, right? So using this this result we have proved, at once we can say AG equals, see, identify the pattern. AG equals, now in both answers L over F1 plus F2 is there, no? In both answers L over F1 plus F2 is there, right? Which means total distance over resultant, times, if you are finding AG, right? If you are finding AG, we got F2, which means if you are finding AG, right, we are going to get Q. And if you are writing BG, total distance over resultant, times, if you are to get BG, it comes to P. So simply keep that in mind as always it is total distance over resultant into the not connected force. What is it? Not connected force means, now if you are finding AG, right? If you are finding AG for this AG section, force Q is not connected, no? So that is coming here. For section BG, force P is not connecting, right? Not connected. So P is coming. We'll be using this as a proved result, and this is called force dividing ratios. And this is called force dividing ratios, right? So take this down as the summary of, write down summary force dividing ratios. Summary force dividing ratios. Take it down. Take it down. Okay, let's see an example. All right, let's see an example. Right, example 1. Take this down along with me. 6 newtons, 4 newtons, and let's say this is 20 meters. Points are A and B. Okay. Now, find distance to point where resultant acts from A. Find the distance to point where resultant acts here from A. Right. Send your answers. Find the distance to the point where resultant acts from A. Right. So simply what I asked is about AG. Okay. Find AG. Quickly. Find AG. Send your answers. Eight centimeters. Yes. So if you need to find AG, right? Since we know the resultant is closer to heavier side, right? I will mark the resultant somewhere here. Resultant is 6 plus 4, no? 10 newtons. 10 newtons. Then if you need AG, apply this theory, proved theory, that's a proved result, right? Total separation 20 over resultant into not connected force. If you are finding AG, the not connected force is here, 4. Right? So that is 8 centimeters, that is correct. 8 centimeters. 8 centimeters, correct. Right? 8 centimeters, right. Next. 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 See? So this is 2 newtons and this force, right, this force is, let's say, 8 newtons and this is 12 meters. Okay, give it a try now. We need AG again. We need AG again. Any answers? Eight meters. See, let's see. Now, in this case, since it is an inclined force, we haven't proved this for inclined forces. This is only valid for two parallel forces, right? Therefore, what you can do is you can dissolve this. Then towards the angle, 8 cos 60 comes. Cos 60 is half. So this is 4 newtons. And away from the angle, 8 sin 60 comes. Right? 8 sin 60 comes. 8 sin 60 comes. Right? When we are applying this, right? We can only focus on these two parallel forces which are acting on the rod, because we know when we are proving this, what we did was go back to our basics. What we did to prove this was writing a force moment about A or B. Writing a force moment about A or B. When we write a force moment about A or B, 8 sine 60 goes through both A and B. So it won't be impacted. But the idea, it won't be impacted. So therefore, we can apply the theory again using 2 and 4. We can apply this again using 2 and 4. Total distance is 12 over resultant of these two, vertical resultant of these two is, right, 2 plus 4, that is 6 newtons. Let's say this is G, right? 6 into not connected force is here 4, right? That is also 8 meters, right? This is meters, yeah, sorry. This is also 8. Okay. Write down below this with the red pen. Since 8 sine 60, since 8 sine 60, since 8 sine 60 goes through, since 8 sine 60 goes through A and B, it won't be impacting, it won't be impacting on force dividing ratios. 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 Right, next. Okay, example 3. See, example 3. Right, this will be the last example before moving on. Right. Right. And let's say this is 10 newtons. 10 newtons. And let me give you the values. Copy it down. Say distance from here to here is 12 meters. Distance from here to here is 12 meters. And distance from here to here is, let's say, 5 meters. Distance from here to here is, say, 5 meters. Okay. Try to apply force dividing ratios here and find AG. Find AG. And I will give you a hint. The hint is, right? The hint is, force dividing ratios are proved only for two forces. That is only for two forces. Only for two parallel forces. Two forces in the sense, only for two parallel forces. Then even if you have more than two forces, if you can narrow down to two forces, you can use this. Right? If you can narrow down to this, you can use this, right? Then as a hint, since you have three forces, if you can apply this like 2 by 2, if you can apply this 2 by 2 for these two forces first, and for the remaining two forces next, still you can use force dividing ratios. Give it a try. I will give you 2 minutes first. Give it a try. Give it a try. Right? 9.33. Let's see. 9.33. Okay, see, now first I'm going to apply, listen, first I'm going to apply force dividing ratios only for these two and find the resultant of these two. That's okay, no? Right? If I need to find the resultant of these two, 2 and 3, we know that is going to be 5 newtons. That is going to be 5 newtons like this. Now, let me label this as ABC, ABC, and this point as G1, this point as G1, right? At once, we can find CG1 using force dividing ratios. No? if I need CG1, total distance between these two forces, 5 meters. Total distance 5 meters over resultant. That is also 5 times. If I need CG1, right, not connected force is 2 newtons. Right? Not connected force is 2 newtons. Not connected force is 2 newtons. Then CG1 is 2 meters. CG1 is 2 meters. Right? CG1 is known. If CG1 is known, now how many forces are remaining in our force diagram? After simplifying the first one, how many forces are remaining now? Only 2 again, because 5 newtons is the resultant of 2 and 3. So 2 and 3 are replaced by 5 newtons. 2 and 3 are replaced by 5 newtons. Right? 2 and 3 are replaced by 5 newtons. And only 10 remains. Now, what if I use force dividing ratios for these two? Right? We can use force dividing ratios for these two now. Right? Now, let's say final resultant is somewhere here. Final resultant is somewhere here. 5 and 10, it should be 15 newtons. No? 15 newtons. Say this is G2. Right? Final resultant as G2, let's assume. Let's assume final resultant as G2. I ask the distance from A, no? Then we need AG2. So before finding AG2, since my two forces are these two now, see? Since my forces are these two now, I need the total distance between these two. This part is 2 meters, this is 12, then this is 14 meters altogether. 14 meters. Right. Now, if I need to find CG2, CG2, no, G1, G2. If I need to find G1, G2, see, this is how we can apply this. If I need to find G1, G2, using the same theory, G1, G2, right? Total separation between these two forces is 14. Resultant is 15 times, right? Times the not connected force. I need G1, G2. So the not connected one is 10. Not connected one is 10. Right? So this cancels by 5, 2, and 3. So it is coming as 14 over 3. What's the value? 14 over 3. 14 over 3 again, 12 over 3 is 4, 20 over 3 is 6.6 is no? Right? So 14 over 3 is 4.6, 4.67. Right? This is 4.67 meters. Now, what I asked was AG2. No? Therefore, see, you can say AG2 equals AG1 plus, right? AG1 plus G1, G2, no? AG1 plus G1, G2. Are AG2 is AG1 plus G1, G2. AG1. Now here we know CG1. CG1 was 2 meters, which means AG1 is AG1 is 3 meters. No? Then AG1 is 3 plus G1, G2. G1, G2 is 4.67. That is 7.67 meters. 7.67 meters. Right? 7.67. 7.67. Is it 20 over 3? 28 over 3? No, no. Different, right? Different, right? Raise your hand if you understood this. The point I need to give you is, right? The point is, even if you have more than, it is not 14 over 3. Sorry, 28 over 3. Oh, sorry. Thanks. 28 over 3. So that is 28 over 3. Yeah, then this changes, this changes. Okay, see? 28 over 3. 28 over 3, that is 9.33. Right. Then this plus 9.33. Final answer 12.33 meters. There 12.33 meters. Right? 12.33 meters. So likewise, the idea I wanted to give here is even if you have more than two forces, right? Likewise, 2 by 2 you can apply. 2 by 2 you can apply. Right? So once you apply for one pair, the system narrows down to two forces again. No? Then again you can apply force dividing ratios. Right? Is it clear? Raise your hand if it is clear. Raise your hand if it is clear. Right. Take it down. Take it down. There's some other method of doing this. I'll explain it hereafter. Right. Take it down. Take it down. Take it down. Okay. See, the other method is we know the principle of force moments now, right? At once we can apply principle of force moments here because that is valid for any number of forces. Right? Give me 1 second. That is valid for any number of forces. Right? If you apply principle of force moments, that is valid for any number of forces. See, now at once we can do this as a method 2 as an alternative method. Now the given system is this. Here 2 newtons, right? This is 10 newtons, and this was 3 newtons, right? 5 meters, 12 meters, right? Now let's assume the resultant of all three is going to act here. 2 plus 3 plus 10, 15 newtons. And if this is A and if this point is G, right? At once we can write force moments considering one point using principle of force moments. Principle of force moments. See? Using principle of force moments. Using principle of force moments. Right, let's write force moments about A because I need the distance from A. Because I need the distance from A. Right? Then resultant. Force moment due to resultant is 15 into distance is AG, no? Right? And it is equal to force moment due to each force about the same point. And about A due to 3 newtons, that is 3 times 5 plus due to 10, that is 10 times 15 plus 12, 5 plus 12, 17. 17. Right? Simplify this. This is divisible by 5, no? Let me divide this by 5 first. Divisible by 5. Then 5 times 2 here to 5 times 3 here. Then it comes to 3AG equals, this is 3. 3 plus 17 over, 17 times 2, 34. It says AG equals 34 plus 3 is 37. 37 over 3. AG equals 37 over 3. 36 over 3 is 12. Then 1 over 3 is 1.33. See, it comes to 12.33 meters. Same answer using a different method. Now, therefore, see that if we have more than two forces, right, that is not that convenient. That is not that convenient and actually shorter, faster if we use force dividing ratios. So therefore, in such cases where we have more than two, where we have more than two parallel forces, we can straight away go with the principle of force moments, right? But yet, this is also applicable. That is also applicable. This is also applicable, right? Usually, this is shorter. Take it down as a method too. Right? That is clear, right? Okay, is that clear enough? Just right? Okay. Write down below with a red pen. Write down below with a red pen. Write down below with a red pen. Even if there are more than two parallel forces, even if there are more than two parallel forces, even if there are more than two parallel forces, even if there are more than two parallel forces, force dividing ratios force dividing ratios are applicable. Force dividing ratios are applicable. Force dividing ratios are applicable by considering forces 2 by 2. 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 Next point, keep using red. Next point. Principle of force moments. 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 Principle of force moments is applicable. Is applicable. Is applicable for any number of forces. Principle of force moments is applicable for any number of forces. Principle of force moments is applicable for any number of forces. Principle of force moments is applicable for any number of forces. For any number of forces, right? Okay, let's move on. Now, see how I'm going to connect this idea with center of gravity. Look at here. See how we are going to connect this idea with center of gravity. See. Now we know what force dividing ratios are. Now let's see how we can connect this with center of gravity. Right? Okay. First write down. Before jumping into calculations, first write down center of gravity of a symmetric object. Write down. Next heading, center of gravity of a symmetric object. Center of gravity of a symmetric object. Center of gravity of a symmetric object. Right. Look at the board. Look at the board. Now let's consider something like a square. Right. So we know these two are symmetric lines. These two are symmetric lines. Right. And let's consider a rectangle. These two are symmetric lines. And if I consider a circle, for a circle, there are infinite number of symmetric lines. There are infinite number of symmetric lines. Right? So likewise, if there are more than one symmetric line, center of gravity is located at the point where the symmetric lines are intersected. Center of gravity is located at the point where the symmetric lines are intersected. Got it? Center of gravity is located at the point where symmetric lines are intersected. Then if we have more than one symmetric lines for an object, no need to do any calculation, right? No need to do any calculation, right? Just identify the point where symmetric lines are intersected. That will be the center of gravity, right? Take down these three. Take down. Write down below. Write down below. Write down below. Center of gravity. Center of gravity. Center of gravity of an object. Center of gravity of an object which has 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 more than one symmetric lines 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 is located at is located at is located at the point where is located at the point where is located at the point where symmetric lines are intersected. Located at the point where symmetric lines are intersected. Located at the point where symmetric lines are intersected. Located at the point where symmetric lines are intersected. Located at the point where symmetric lines are intersected. Right? Okay. Now, what happens if the object has only one symmetric line? Such objects are there. Right? They have only bipartial symmetricness. Bipartial. Right? You know what bipartial means, right? Bipartial symmetricness. Now, in such kind of a case, right? In such kind of a case, say now for an object like this, see, for an object like this, it has only one symmetric line goes through this, and for an object like this, see, it has only one symmetric line goes through this. For an object like this, like this, it has only one symmetric line. In such cases, listen, in such cases, without doing a calculation, we can't exactly say where the center of gravity is. But there's one thing that we can say, that is, if there is only one symmetric line at least, center of gravity center of gravity will be on a point which is on the symmetric line. But we can't say at which point on the symmetric line without doing a calculation. For that, we will be doing a calculation. Right? We can't say at which point on the symmetric line without doing a calculation. For that, we will do the calculation. Right? But if there is only one symmetric line, we can say, right, center of gravity is located on the symmetric line. On the symmetric line. Take it down. Take it down. Write down below. Write down below. Write down below. If there's only one symmetric line for an object, if there's only one symmetric line for an object, if there's only one symmetric line for an object, if there's only one symmetric line for an object, center of gravity is located, center of gravity is located, center of gravity is located on that symmetric line, center of gravity is located on that symmetric line, center of gravity is located on that symmetric line, center of gravity is located, center of gravity is located on that symmetric line, center of gravity is located on that symmetric line, closer to heavier side, closer to heavier side, right? Closer to heavier side, within brackets, a calculation should be done, within brackets, a calculation should be done, a calculation should be done to identify, a calculation should be done to identify the exact point. A calculation should be done to identify, a calculation should be done to identify the exact point. A calculation should be done to identify the exact point. A calculation should be done to identify the exact point. Okay, clear? The last case is if the object don't have any symmetric line, right? Something like this. See, object has no symmetric lines. Object has no symmetric lines. In such cases, what we do is, right, we'll be doing a calculation again, right? Calculation again, and then only we can say where the exact center of gravity is. Otherwise, if there are no any symmetric lines, we can't predict center of gravity. You can't predict where the center of gravity is, right? Take this down. Write down. Write down these three. Write down these three. Write down below. If the object has no symmetric lines, 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 center of gravity should be identified, center of gravity should be identified, center of gravity should be identified, center of gravity should be identified through a calculation only. Center of gravity can be identified or should be identified through a calculation only. Center of gravity should be identified through a calculation only. can be identified through a calculation only. Right? It can be identified through a calculation only. Okay. Okay. Let's move on now. Okay. See, we have this kind of a scenario. We have a scenario where two metal balls are connected to a light rod. Two metal balls are connected to a light rod, right? So let's say this ball is 12 kilograms and this ball is 8 kilograms. It is connected using a light rod of length 10 meters. Right. Now, listen. Example 1. Listen. Weight of 8 kilograms is 80 newtons act here. Weight of 12 kilograms is 120 newtons act here. Right? Center of gravity is, listen to these words carefully. Center of gravity is the point where weight of an object acts. Then if I convert that to a system, center of gravity of a system is the point where resultant weight of the system acts. Right? Center of gravity of a system is the point where the resultant weight or the total weight of the system acts. Now, since the rod is light, total weight is given by these two. Then, if we can find the point where, the resultant of these two acts on this system, that is the center of gravity of this system. That is the center of gravity of this system. Correct? For an object, that is the point where weight acts. If I convert the same idea for a system, right, that should be the point where the resultant weight of the system acts. Right? Now, the resultant of these two will be closer to heavier side, 120, 200 newtons. Right? And the point where this resultant weight acts on the system, this point where the resultant weight acts on the system is called center of gravity. Right? Now, to find center of gravity in such kind of a scenario, we can make use of the force dividing ratios that we just learned. Right? Take it down, and find distance from, let me label this as A and B. Find the distance to center of gravity from B. Find the distance to center of gravity from B. Take it down and find it out. 4 meters. Right. Now, if I apply force dividing ratios again, Bg, right? That is why we have force dividing ratios, Bg. Total is 10 over resultant 200 into not connected force 80, right? 0 to 0 cancels, right? By 4 we can cancel 4 times 2, 4 times 5, right? Then 5 times 2 here, 4 meters. 4 meters. Got it? Which means center of gravity of this system is located 4 meters from point B. Got it? And label this as a light rod, otherwise you will get confused. Label this as a light rod, a light rod, a light rod, light rod. Okay, write down below, write down below, write down below. The point where resultant weight, the point where resultant weight, the point where resultant weight slash total weight, the point where resultant weight slash total weight of a system acts. The point where total weight slash resultant weight of a system acts should be the center of gravity, should be the center of gravity of system, should be the center of gravity of system, should be the center of gravity of system. Right. Listen. Now we are going to carry this same idea forward to determine the center of gravity of other combined objects. What are combined objects? Combined objects means if an object is made using two or more than two standard shapes, right? Standard objects, we call that a combined object, right? As a next topic, write down determination of center of gravity, determination of center of gravity of combined objects, determination of center of gravity of combined objects, determination of center of gravity of combined objects, right? Listen. So for this purpose, basically we categorize our objects into 3 categories, right? Object and the volume, right? See, first look at here. First type of objects are wires or rods, right? When we are given as a wire or a rod, we don't consider its cross-sectional area. Always by default, we consider this as a thin wire and a thin rod, right? We consider it as a thin wire and a thin rod. If cross-sectional area is given, you can consider, right? What I mean is, if the cross-sectional area is not given, without giving the cross-sectional area, if it is given as wires or rods, if it is given as wires or rods, we will be considering, listen, we will be considering length as volume, length instead of volume, because the reason is, if there is a very thin wire, there is no cross-sectional area, very thin, then only a length is there, then in that case, instead of volume, right, for the sake of finding mass, we are using lengths, right, something like that. And the other type is discs and plates, right? distant plates. They have only an area because their thickness is negligible. Then instead of volume, we consider area in such cases, right? And here, if there is a 3D object, right? 3D object, 3D or volumetric, then only we consider volume, right? So this basic standards and the procedure will be followed when we are writing masses in the coming parts of the center of gravity, right? So write down, before this, write down, objects are categorized to 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 three main categories based on the parameter to be considered, based on the parameter to be considered, based on the parameter based on the parameter based on the parameter to be considered, based on the parameter to be considered when finding mass, based on the parameter to be considered when finding mass, within brackets write down, mass equals 0, within brackets write down mass equals 0, within brackets mass equals 0, within brackets mass equals 0. Right, now take this down, take down the table, take down the table, take down the table. Take down the table. Right, take down. Right, listen, and this is how we are going to apply this. I will show you how to apply this using examples. Right, now look at here. We are slightly moving towards, right? We are gradually moving towards the advanced parts of center of gravity. Right, now we are still at the determinations of center of gravity using calculations. Right, and there are a few more things, coming up about maximum ranges when falling objects using center of gravity, right? Maximum displacements, maximum ranges, finding center of gravities, and predictions in the sense guessing center of gravity, right? Without doing a calculation. So there are things, right? Now let's say we are given a system like this. This is a wireframe of side length. This is a wireframe of side length. Let's say 2A. A wireframe of side length 2A. A wireframe of side length 2A. It is attached with another wire of length 2A. With another wire of length 2A. Right. And let's say this point is point A, and this point is point B. Okay. First tell me, how many symmetric lines for this given object? How many symmetric lines for this given object? How many symmetric lines for this given object? Quickly. 0, 1, 2. What are the answers? 0 or 1 or 2? How many symmetric lines? Quickly. There's only one. Right? So this is a symmetric line. Only one symmetric line. Only symmetric line the object has. Right. Now, from our previous series, we know if it has only one symmetric line, center of gravity should be a point on the symmetric line. Now, after doing a calculation, what I'm trying to do is to determine the exact point on this line. Right. For that, now say this is a wireframe. Right. This is a wireframe. This is a wireframe. A wireframe. This is a wireframe. Now we are here. That is wires. Then to write mass, we are going to consider length. If the length is known, length into rho gives us mass. Right? See, now I'm going to write the mass of this object. Now, first I can see this is made of two separate objects. One is a square, the other one is a wire. Right? One is a square shaped wire part, and the other part is a wire of length 2A. It consists of just two standard shapes. Right? Then we can write the weight of this wireframe. Because m equals 0. Right? M equals 0. See how this is applied. M equals 0. Let me do it somewhere here since this is the first one. M equals 0. Right? Then mg equals 0g. Right? Now I need mg. But instead of v, we will be writing the length. Length of this wire is 8 no? Then 8 rho g. Got the idea? 8 rho g. Now, this weight can be written as 8 rho g. Similarly, this weight can be written as 2a rho g. Right? 2a rho g. Center of gravity of these two should be in between, no? Because these two are two parallel, not perpendicular. These two are two parallel weights which are acting at these 2 points. Then center of gravity should be in between because the resultant of these two is going to be in between. Center of gravity of the system is the point where total weight or the resultant weight acts on. Then the resultant of these two is in between for sure. And since 8 is heavier, it should be closer to this side. That we can guess. It should be closer to this side. Right? It should be closer to this side. And the resultant is 10a rho g. Resultant is 10a rho g. Resultant should be 10a rho g. Right? 10a rho g. Now, if this point is g, right, at once we can find ag, right, using our force dividing ratios. That's why we have proved force dividing ratios. Ag can be written as total between these two. This part is a, this is also a, then 2a. Right? Make a 2a from here to here, total distance 2a. Right? Over resultant 10a rho g. 10a rho g. If I need ag, the not connected one is 2a rho g. A rho g cancels. Right? Then ag equals 2 times 5, 2a over 5. That is 0.4a, 0.4a, which means center of gravity of this system is now located 0.4a distance, 0.4a distance away from A. Got my point? Now, likewise, when the combined object is given, now this is a combined object. When the combined object is given, and if it has only one symmetric line, for sure we know the center of gravity is on the symmetric line, right? Since that is on the symmetric line, by a simple calculation like this, we can determine what is the exact point of the center of gravity on the symmetric line. Raise your hand if this is clear. Raise your hand if this is clear. Okay, right, good. Take it down. Take it down. Give me 2 minutes. I'll fill some water and come back. Right? Right, it's clear, right? 0.4a, 0.4a from this point. So likewise, easily we can find the center of gravity of the combined object using these theories. Right, now still it should have at least one symmetric line. It should have at least one symmetric line, right? There are methods to find without any symmetric line as well, right? So we are moving towards those parts, right? We are moving towards. Okay, let's try another one. Let's try another one. Example 2. Example 2. Example 2. See, Example 2. Two wire frames. Two wire frames of radii R and R over 2 are connected together like this. Right. If this center is A and if this center is B, find distance to center of gravity from A, AG. 2 minutes. Right. Send your answers. Send your answers. Okay, let's see. 0.5 R. 0.5 R. Let's see. They are wires. So wires means we are considering the length when writing volumes. Right? We consider the length when writing volume. We consider the length when writing volume. Right? Length of this is 2 pi R. Then 2 pi R rho g. And length of this one is 2 pi R is R over 2 rho g. These two cancels. Resultant will be somewhere in between. Right? That is 2 pi R rho g plus 5 R rho g, 3 pi R rho g. 3 pi R rho g. Right? I need what? AG. We need AG. In AG, total distance R plus R over 2 over resultant 3 pi R rho g into, if I need AG, not connected one, 5 R rho g. 5 R rho g to 5 R rho g cancels. Then AG equals R plus R over 2 is 3R over 2. Right? That is 3R over 2 over 3. Right? Yes. Simplify this. R over 2. R over 2. R over 2 means 0.5 R. Correct. Good. R over 2. Right? One more example. Next one. Okay. Say these two are two discs. Say these two are two discs. These two are two discs of radius 2R and R. A and B. Right. They are discs. Discs. Right. Find center of gravity. Distance to center of gravity from A. Give it a try. Find distance to center of gravity from A. Find distance to center of gravity from A. Give it a try. Find distance to center of gravity from A. Send your answers. Okay, any answers? 0.6. 0.6 are. Let's see. Let's see. Now they are disks. If they are disks, we know we are to consider area now. We are to consider area now when writing volumes, when writing the volume. Then this can be written as 0g, but the area now is 5r squared. R squared is 2r squared rho g, right? And this is 5r squared rho g. And the total is resultant is this is 4r squared rho g, no, with this 5r squared rho g, 5r squared rho g, 5r squared rho g. If you simplified this, right, if you simplified this, you will get 4 5r squared rho g, right? Okay, now let's say this is g. Apply our theory again. Ag can be written as total. Total is 2r plus r, 3r over resultant 5r squared rho g times not connected force is this one 5r squared rho g, 5r squared rho g, 5r squared rho g, 5r squared rho g to 5r squared rho g cancels, right? Then this is 3r over 5. That is correct. 3r over 5 can be written as 0.6r. Good. Good. Let's try one more. Let's try one more. Now let's try two more. Another one from the volume. See. Now same thing. What if this was spheres? Right? They are spheres. Spheres. Same dimensions. 2r and r. Say these points are A and B. Find center of gravity here. Find the center of gravity from A. From A. Right. Send your answers. One over 3r. Let's see. 1/3r. Okay, let's see. Now, if they are spheres, they are 3D objects, 3D volumetric. Then have to consider the volume itself. Right? Volume. This volume is, we know volume of a sphere is, right? Additional knowledge, additional volume of a sphere is 4/3 pi r cube. 4/3 pi r cube. Right? Now here, this should be 4/3 pi r. R is 2r now. 2r cube. Since 4/3 pi is going to be common for all, since 4/3 pi is common to all, going to be common for all, right? Without simplifying it, I'm going to keep it. Then this is 8r cube rho g. And this one here, this is 4/3 pi r cube rho g. And the resultant will be in between. Resultant will be in between, right? And that is, if this is 4/3 pi 8r cube, this is r cube, then this should be 4/3 pi 9r cube rho g, no? Right? 4/3 pi 9r cube rho g. Now, if I apply force dividing ratios to find Ag, right? Same application in terms of the force dividing ratio. Ag equals total distance is 2r plus r, 3r, right? And resultant is 4/3 pi 9r cube rho g times if I need Ag, the not connected one is 4/3 pi r cube rho g. 4/3 pi r cube rho g. Right? See, 4/3 pi to 4/3 pi r cube rho g to r cube rho g cancels. Right? Good. Ag equals 3r over 9. Right? So that is r over 3. Good. That is r over 3. R over 3. Right? You got the answer now? Good. R over 3. Right. And I will do one last one before moving on to the next part. One last example before moving on to the next. Five. These are laminas. What is a lamina? What is a lamina? What is a lamina? Lamina is a disc. Lamina means discs. Right here we have 3 discs of radii 4r, 2r, and r. Right. So let's say these points are A, B, C. Right. A, B, C. A, B, C. And this one is X. And this point is Y. Okay. This is a question. The question is find distance to center of gravity of combined object from X. Start now. From X. Start now. Start. Start now. Now you know how to deal with three parallel forces when you have, right? You know how to deal with three parallel forces when you have. Use those things. right? Okay, 7.7.14 R, 7.14 R. Okay, let's see. Now, by the end of the class today, we'll be covering all theories of center of gravity, right? Which means next day will be a full day of questions of center of gravity, right? Therefore, today these things are the foundation. These things will lay off the foundation for all the center of gravity questions, all types of questions which are going to come up next day. Correct? Right? Now, today also I'll be discussing along with examples, right? But specifically, next day will be allocated for all the types of questions. Now here, for the examples, I'm using like simple and average questions and all other question types, right? With combinations and everything will be discussed exclusively on next day, right? So therefore, knowing these theories, understanding the theories to the fullest is compulsory, right? To next day things. Okay, let's see. Right, look at here. They are disks. If they are disks, this is 5r squared, no? Right, 5r squared rho g. Then this is 5r squared is 4r squared, 4r squared rho g. And this weight is 5 r squared is 16r squared rho g. And this one 5r squared rho g. Right. So we don't know from which point the resultant acts. Right? We don't know. We don't know from which point the resultant acts. So let's mark the resultant somewhere here. This is a random point. This is a random point. Let's mark the resultant somewhere here. Right. So these numbers are 4, 16, and 1. Then that is altogether 21. That is altogether 21. No? Then this is 5, 21 r squared rho g, isn't it? 5, 21 r squared rho g. 5, 21 r squared rho g. Right. Now, if I need the distance from x at once, use principle of force moments. Using principle of force moments. Principle of force moments. Right. Using principle of force moments. And force moment about x of resultant should be equal to force moment about x by each force. Right. From the resultant, that distance is xg, no? Right? Xg. And this is 5, 21 r squared rho g times xg. And there are three forces which create the force moment about this, right? One is this 5, 4r squared rho g. 5, 4r squared rho g times distance is 2r plus from this one 5, 16r squared rho g. 5, 16r squared rho g. The distance is up to here, that is 4r, 4r plus 4r, 8r plus last one 5r squared rho g, 5r squared rho g. The distance up to here is 4r here, 8r here, 12r, 13r, 13r, 13r. Right? Now 5r squared rho g, 5r squared rho g cancels throughout. Phi r squared rho g, phi r squared rho g cancels throughout. Right? Simplify. Then 21 xg remains. 21 xg remains. Right? And here 4 times 2r, 8r remains. Right? And here 16 times 8r, 16 times 8r, 128, right? 128 r plus here 13 r, then 21 xg equals 8 plus 128 is 136. 136 plus 13 is 149. 149 r. So xg equals, this seems divisible. 149 over 21. Is it divisible? Is it divisible? By 3? No, by 3. Yeah. Yes. By 3 this cancels. By 3. Make 3 times. 149. 3 times 70. 3 times 120 again it is 40. No. 40. By 3 will not bad. No, it is not going to divide. It is not going to divide. Not going to divide. Then hereafter we have to do a simplification and see. 149 over 21. Is that what you got? 7.09. 7.14. What's the difference? 7.095. 7.09 R. Isn't it? Isn't it 7.09? Yeah. Okay. Take it down. Likewise, even if we have like more than 2 or 3, 4, 5, 6, any number of forces, this is applicable, right? Principle of force moment is applicable. So at once we can find it out. Take it down. Take it down. Take it down. Take it down. Right? Okay, right. Let's move on. Any questions up to here? Any questions up to this point? Any questions up to this point? Any questions? Any questions up to this point? No? Is it all clear? Any questions up to this point, or is it all clear? Clear. Right. Let's move on. Let's move on. Next topic, write down. Center of gravity of a triangle. Next topic. Center of gravity of a triangle. 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 Next heading. Center of gravity of a triangle. Right? Center of gravity of a triangle. Okay, listen. So when it comes to a triangle, there is a separate, a unique method, a separate and a unique method to find center of gravity. It is like this. For any kind of a triangle, for any type of a triangle, right? For any type of a triangle like this, for any type of a triangle like this, right? If we draw its angle bisectors, let's say this triangle is ABC. We draw its angle bisectors like this, right? All angle bisectors, right? All three angle bisectors intersects at the same point. All three angle bisectors of a triangle intersects at the same point. All three angle bisectors of any triangle intersects at the same point. Right? This point is called center of gravity of the triangle. And there are more important things. Any angle bisector divides by the center of gravity in 2 to 1 ratio. Always the vertex side is 2, this side is 1. Vertex side is 2, this is 1. 2, 1. So likewise, it divides the angle bisector in 2 to 1 ratio. Right? For any kind of a triangle, any type. Right? Doesn't matter whether isosceles or right angled or equilateral law, whatever it is, for any triangle, for any triangle, this is a method. Right, take it down first. Write down. Right, write down below. First point. Center of gravity. First point. Center of gravity of a triangle is. Center of gravity of a triangle is. Center of gravity of a triangle is located at center of gravity of a triangle is located at center of gravity of a triangle is located at the intersection point at the intersection point located at the intersection point located at the intersection point of angle bisectors of all three angle bisectors of all three angle bisectors intersection point of all three angle bisectors, right? Intersection point of all three angle bisectors. Right. Next point, as the next point, write down. Next point, center of gravity divides. Center of gravity divides. Write down. Center of gravity. Center of gravity divides. Center of gravity divides. Divide any angle bisector. Divides any angle bisector. Center of gravity divides any angle bisector. Center of gravity divides any angle bisector. Center of gravity divides any angle bisector in 2 to 1 ratio. Any angle bisector in 2 to 1. Any angle bisector in 2 to 1 ratio. Center of gravity divides any angle bisector in 2 to 1 ratio. Center of gravity divides any angle bisector in 2 to 1 ratio. Center of gravity divides any angle bisector in 2 to 1 ratio. In 2 to 1 ratio. Right? Highlight to underline 2 to 1. Highlight to underline 2 to 1. Highlight to underline 2 to 1. Okay, listen. Now, for these specific triangles, look at here. For these specific triangles, now as examples, fine. As examples, say this is an isosceles triangle. Say this is an isosceles triangle like this. Isosceles triangle. Isosceles. Right now, in that case, we know. In that case, we know one angle bisector will be like this, and it is perpendicular to this. One angle bisector is like this, perpendicular to this, and in that case, now center of gravity must be, if you connect these two also, this is how it will be, and center of gravity should be, must be somewhere here, as this is divided as 2 to 1, as this is divided as 2 to 1 in the ratio 2 to 1. Now, if the height of the triangle was h, if the height of the triangle was h, right? Using that, we can say if this ratio is 2 to 1, this has to be 2h over 3, and this has to be h over 3. Right? You know how to convert a ratio to a fraction, no? You know how to convert a ratio to a fraction. Now the ratio is 2 to 1. Ratio is 2 to 1, right? 2 to 1 means 2 plus 1 is 3. So 2 over 3 is here, and 1 over 3 is here, like this. Right? Take it down as example 1. So this is how we are going to use these ideas. This is how we are going to use these ideas. right? Now, if this is an equilateral triangle, see, if this is an equilateral triangle, equilateral triangle, right? So we know this is how these angle bisectors are. This is how these angle bisectors are, right? Say side length of this triangle is A. Side length of the triangle is A. Okay. If side length of the triangle is A, if side length of the triangle is A, can you find BG? Can you find BG? Try this out. Oh, sorry, not BD. Let's say ABC, ABC, D. Can you find DG? Give it a try. Give it a try. Find DG. Now, about a center of gravity of a triangle, there are specific theories. Now, we are using those specific theories to find the center of gravity. Right? Find DG of this triangle, that is equilateral. Equilateral. 2 minutes. Right? Give it a try. Any answers? right? Any answers? DG. So it should be something in terms of A. Should be something in terms of A, as we did here. Now here, this value was HO3 and this is 2HO3. No? So likewise, I need DG now. I need DG. DG. Root 32. What do you say? Rasmita, any answers? Right. Try to use your basic geometry knowledge. Use your basic geometry. Use your basic geometry. Use your basic geometry. Use basic geometry. Okay, see. Now, if there is an equilateral triangle, one angle of the triangle should be 60. Now, I have drawn an angle bisector. Then that angle bisector divides 60 as 30 and 30. Then one angle here should be 30, no? Right? One angle here should be 30. Should be 30. Right? And the angle here is also 30. Right? And since this is an equilateral triangle, listen, since this is an equilateral triangle, this divides, this angle bisector divides this side also to two equal parts, isn't it? This divides this side also to two equal parts because these two triangles are congruent triangles. Congruent in the sense they are same triangles. Congruent again, you know, right? From all levels, congruent triangle. 30, 30, same side here, same sides are here. Then for sure these two sides should be equal. Then these two are also equal. Now we have a small triangle here. No? We have a small triangle here. From this triangle, now this is C, this is D, and this is G. From this triangle, this angle is 30, right? And if side length is A, this has to be A over 2. No? This has to be A over 2. If the side length is A, this is A over 2. If the side length is A, this is A over 2. Right? Now, what did I ask? I asked this. So let's say this is X. dg equals x, if that is x, why can't we write a trigonometric ratio as you can get x, right? Now, what if I write tan 30, right? Look at here. What if I write tan 30? Tan 30 equals x over a over 2, no? X over a over 2, opposite side to adjacent side. Tan 30 is a known value. Tan 30 is a known value. 1 over root 3. Tan 30 is a known value, 1 over root 3. Right? This is x over a over 2, then 2 goes here, like this. We need x. And x equals a over 2 root 3. Isn't it? X equals a over 2 root 3. So likewise, using some sort of geometry, and this knowledge we have, right here, and this knowledge we have on these things, right, on these things, we can easily find it out like this. And now if needed AG, say now you need AG. Now what about AG? Now this is BG, yeah, sorry, DG. Therefore, DG equals a over 2 root 3. Now, what if you wanted to find AG? Now we can get AG. Simply by using this, because this is only 1/3 here, no? This divides in 2 to 1 ratio. Only 1/3 is here. Only 1/3 is here. Then this should be the 2/3 of that, no? 2/3 of that. Which means if this is 1/3, right? 2/3 of this is the other one, right? Then AG should be a over 2 root 3 into 2, no? Is it clear? Because they are in this ratio. 1 to 2. Then if DG is 1, 2 of this ratio is this. These two cancels, right? So AG comes as a over root 3. Alright. So likewise, using these theories we know, basic geometry, in addition to these theories we learn about center of gravity of a triangle, right? We can find the center of gravity of a triangle like this. Raise your hand if it is clear. Okay, right. Take it down. And there are many more options, right? There are many other ways as well, right? If you use this type of a triangle, listen, right? So it is up to you. As long as you follow a proper method, you will get the same answer. On a triangle use this one. Side length is A, right? And this total angle is 60. This is A over 2. Use if you know the total distance from A to D, DG is 1/3 of AG, no? 1/3 of AD, no? There are many more methods, many more options. Right? Take it down. Sometimes you might have tried in a different way. So if there is a different way, after copying this down, you can again try out using your method if needed. Right? There are more ways to do. This can be done using dissolved components as well. Right? Using dissolved components, right? Some other triangles. There are more other ways. Right? Take it down. Listen. Right. Listen. Now we are like more than halfway through. We are like around 65%, 70% of theories are covered now, right? Around 65%, 65, 70% of theories are covered now, right? And now we are going to have a break. So after the break, again, we'll be extending our discussion towards the other types of uh, examples we can have in center of gravity, especially balancing objects. Balancing objects means balancing objects without being unstable, like this. Balancing objects without being unstable based on center of gravity. That's the main part to be covered after the break, right? So we'll get a break. We'll get a break of 20 minutes, 20 minutes and regroup. Right now it's 11:57. Right, we'll get a break of 20 minutes. You can leave and come back. Now it is 11:58, and we will regroup at 12:18. And we will regroup at 12:18. Right. So by the end of today, by the end of today, by the end of the class today, by the end of the class today, we'll be covering all theories in center of gravity. Right. So this is comparatively a small part, a small lesson. Right. Then by next day, we'll finish off everything. Right. Okay. So let's have the break and regroup. Okay, am I audible? Yes, right. One more second. One more second. Right. Right, we'll start. Okay, now with the idea about a center of gravity of a triangle, we just learned norm, right? So let's see one more question before moving on. Right, one more question before moving on. Right, from this idea we just learned. Okay, see, this is a question. This is a question. Right, write down, write down, write down. A square of, write down. A square of, a square of, a square of side length a square of side length a square of side length is connected to a square of side length is connected to a square of side length is connected to an equilateral triangle of connected to an equilateral triangle of connected to an equilateral triangle of an equilateral triangle of side length A as shown. An equilateral triangle of side length A as shown. an equilateral triangle of side length A as shown. Find the distance to center of gravity. Find the distance to center of gravity of object. Find the distance. Find the distance to center of gravity of object. Find the distance to center of gravity of object from point B. Find the distance to center of gravity of object from point B. Find the distance to center of gravity of object from point B. Find the distance to center of gravity of object from point B. Okay, start now. Start. Start now. Start it. Okay. Send your answers. Saravanan. Hi, how are you? Any answers? Give it a try. Give it a try. Now, this is a combination of what you have learned so far. It's a combination of what you have learned so far, right? In the previous part, we did some calculations on this, and now this is connected with the triangle. Now it is connected with the triangle. Connected with the triangle. I need distance from B, right? We need distance to center of gravity from B. We need distance to center of gravity from B. Any answers? Any answers? Any answers? Root 3a. First class is root 3a. Root 3a from b. A possible value. We'll check. Good. I will start in 2 minutes. Root 3a. Let's see. Same here. Right. Let's see. Let's start. Right. Now they are squares and triangles, so which means they are plates, discs. Right? Discs. Then center of gravity of the square is at its center. So weight x, right? Center means the line where the point where the symmetric lines are intersected, right? And since they are discs or laminas, right? They are laminas, no? They are lamina, which means we are going to consider area. Right? This area is a times a squared, then a squared rho g, right? And this one, weight of this one is, we know area of a triangle is half into a into this height, half into a into this height, perpendicular height. Now we have to first know the perpendicular height. That is a equilateral triangle. Then this one angle is 60 each, 60. So if this is a, this can be written as, using our dissolved components, this can be written as, if the diagonal is a, if the hypotenuse is a, right? This can be written as a sin 60. A sin 60. Right? A sin 60. Then 2a into a sin 60 rho g. Right? So if I simplify this a bit, what comes is a squared sin 60 is root 3 over 2, root 3 rho g over 4. Right. Now the resultant should be somewhere in between. It should be somewhere in between. Right. Now from this, if a squared rho g is taken out, that is for 1. Right. 1 plus root 3 over 4 remains. 1 plus root 3 over 4 remains. Right. Now we need distance from B. That is BG. Right. We need distance from B. Right. Now, if we are using force dividing ratios, right, we can get the distance from here to here first, and then this part should be added. Right? We can get the distance from here to here first, and this part should be added. Right? So let's see how we can do. Now, for that, let me label this point as C. Then first I can find CG using force dividing ratio. CG. Total distance between these two, right? Total is, this is only a over 2. This part is a over 2, and this divides the center of gravity, right? This bisector is divided by the center of gravity in 2 to 1 ratio. Then this side we have a over 3. Then a over 2 plus a over 3. Total distance is a over 2 plus a over 3. Whole thing over resultant a squared rho g 1 plus root 3 over 4. times, if I need CG, the not connected one, A squared rho G. Right? A squared rho G. Now these two cancels. CG comes here, common denominator is 6. 6. Then 3A plus 2A, 5A. Right? And here we have common denominator is 4. Then 4 plus root 3. 4 plus root 3. Simplify. This can be written as 5A over 6 times 4 over 4 plus root 3. By 2 this cancels, 2 times 2, 2 times 3. Right? So this is 10A over 10A over 3 times 4 plus root 3. Right? This is CG. 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 The final answer I need is BG. BG can be written as BG can be written as BC plus CG. BC plus CG. Right? So BG can be written as BC. What about BC? BC was 2A over 3, no? With the ratio. With the ratio, this is 2A over 3. 2A over 3 and A over 3. 2A over 3. Oh, sorry. Sorry, there's a mistake. A sin 60. Root 3 is missing. See? So let me do that correction. Now this should be 1/3 of A sin 60, no? Then A sin 60 over 3, not A over 3. A sin 60 over 3. A sin 60 over 3. Right? This is 2A sin 60 over 3. Then this will be changing. Let me correct it again. See? A sin 60 over 3. Then A over 2 plus this total distance is different. A over 2 plus this part is A sin 60 over 3. A sin 60 over 3 over total A squared rho G 1 plus root 3 over 4 into not connected force A squared rho G. Right? Now it's correct, right? Now it's correct, no? Right. Then these two cancels. Simplify. This is A over 2 plus sin 60 is root 3 over 2. That is root 3A over 6. Root 3 over 6. Right? Whole thing over. Common denominator here is 4. Right? 4 plus root 3. Right? Now we can rewrite this as 2 and 6 means common denominator is 6. 6. Then 3A plus root 3A times 4. 4 plus root 3. Right? Okay. Now these 2 and 3. 2 and 3. 2 and 3. Right. So here it comes as 2A times, right? 2A is taken out. 3 plus root 3 over 3 times 4 plus root 3. This is our CG now. Right? This is our CG now. Do the same now. Do the same as we were trying to do before. Right? BG can be written as BC plus CG. BC plus CG. Right? Then BC is here. BC 2A sin 60 over 3. 2A sin 60 root 3 over 2 over 3 plus CG is here 2A 3 plus root 3 2A 3 plus root 3 over 3 plus 3 times 4 plus root 3. Right. Then do the possible simplifications. Okay, this common denominator is, see, this is 2 root 3A. sorry, 2 cancels. 2 cancels. So this is root 3a over 3. This is root 3a over 3 plus. This is nothing cancels. 2a 3 plus root 3 over 3 times 4 plus root 3. Common denominator should be, right? Common denominator should be this one, and simplify the numerator as much as possible. Now this is 3 times 4 plus root 3. Then this should be multiplied, root 3a should be multiplied by 4 plus root 3. Plus this part is still there, this is still there, 2a times 3 plus root 3, right? Since a is common, right, if I take a out from everything, right, 3, 4 plus root 3, right? And be careful with the simplification here. See, root 3 into 4. What is the term? 4 root 3. Root 3 into 4. The term is 4 root 3. And root 3 into root 3. The term is 3. And here 2 times 3, 6. Right? Then 2 times root 3, 2 root 3. These terms are coming. These terms are coming. Right? Now, 4 root 3 plus 2 root 3, 6 root 3. 3 plus 6, 9. Right? Over. This same thing remains. 3, 4 plus root 3. And out of everything, a. Right. It is simplifiable further. Now a 3 is common. Now a 3 is common. Right? 3 is common. Take it out. Then 3a. Right. Let me do here 3a. 3a. And from there are 2 root 3 plus 3. 2 root 3 plus 3. Right? Plus 3. And over 3 plus 4 root 3. 3 plus. Sorry. 3 times 4 plus 3 times 4 plus root 3. Now 3 to 3 cancels. Final answer is this. Final answer 2 root 3 plus 3 over 4 plus root 3 times a. Final answer. Right? See how the simplification goes. See how the simplification goes. Right? Copy it down. So while copying down, be vigilant and try it and check whether there are any mistakes and you are getting the same. Write it down. See, this is how this changes if we combine these two together, right? So in terms of simplification and everything, it makes it more complex. It makes it more complex, right? This is the final answer. Take it down. Right? Don't just copy it down. Simplify from your side also and check with my answers. right? Right? Finish? Finish? Write it down quickly. Okay, finish? Did you finish? So if you are still trying, try it. Because it is a simplification that we should do, right? That's a simplification that we should do, right? So in terms of the simplification, there is something to do here, right? Dissolved components are also used, right? See how this idea is like connected together and we use it in the question. Right? See how the idea is used. Okay, write down below with a red pen. Write down below with a red pen. Write down below. Write down below. Write down below with a red pen. Write down below with a red pen. Write down below with a red pen. Center of gravity of triangle. Center of gravity of triangle. Center of gravity of triangle. Center of gravity of triangle divides. Center of gravity of triangle divides divides center of gravity of triangle divides its perpendicular height divides its perpendicular height divides its perpendicular height divides its perpendicular height in 2 to 1 ratio divides its perpendicular height in 2 to 1 ratio divides its perpendicular height in 2 to 1 ratio divides its perpendicular height in 2 to 1 ratio. Right, let's move on. Right. As the next topic, write down. As the next topic, write down balancing of objects. Write down balancing of objects. Next heading, balancing of objects. Balancing of objects. Balancing of objects based on center of gravity. Balancing of objects based on center of gravity. Balancing of objects based on center of gravity. Right, look at here. Okay, now to recall the things we start off with, tell me now, based on the location of center of gravity, how many equilibriums are there? How many equilibriums? There are 3 equilibriums. Right? One is stable. Stable is when the center of gravity and the acting line of weight is inside the border. Right? And then neutral equilibrium. Neutral equilibrium is when center of gravity or acting line of weight is at the end of the supporter, at the edge of the supporter, at the end of the supporter or at the edge of the supporter. Right? And if center of gravity or acting line of weight is outside the supporter surface, that is not an equilibrium. For sure, that object is going to fall. Right? So with that, we identified that the minimum point or the minimum condition, the last point that we can keep an object in equilibrium is neutral. Right? The last point we can keep the object in equilibrium is the neutral condition. Right? So therefore, if we need to maximize or minimize lengths or something like that, right, always we'll be focusing on that neutral state, because that is the last point of equilibrium. No? If I ask to maximize something, then that is how it is connected. Right? Okay, let's see with an example. Let's see this with an example. Right. Say this is a table. And these two books are kept on a table. These two books are kept on a table like this. These two books are kept on a table. This is a table. These two books are kept on a table. Right? Say they are identical, two identical books of length of each, say 12 centimeters. Right. And let's say this point is point A, right, B and C. As an example, write down first this. As an example, write down two identical books. Write down two identical books. As an example, write down two identical books of each length, 12 centimeters. Two identical books of each length, 12 centimeters. Two identical books of each length, 12 centimeters. 12 centimeters is placed. Sorry, are placed on a table. Are placed on a table. Are placed on a table. Are placed on a table as shown. 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 What is the maximum? What is the maximum? What is the maximum? What is the maximum distance can be gained? What is the maximum distance that can be gained? What is the maximum distance? What is the maximum distance? Can you make maximum horizontal distance? What is the maximum horizontal distance? What is the maximum horizontal distance? Maximum horizontal distance that can be gained. What is the maximum horizontal distance that can be gained between points A and C? Between points A and C. 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 As books are safely on the table without falling. As books are safely on the table. As books are safely on the table. As books are safely on the table. As books are safely on the table without falling. As books are safely on the table without falling. Okay, take down the diagram. Take down the diagram. I will explain since this is the first one. Right. Listen now. Now, one of the most important words we have here is maximum. One of the most important words we have here in the question is maximum. Right. Maximum. Tell me, if we need to increase these lengths to their maximum values, what is the last point of equilibrium we can have? Because I say this should be without falling. This should be without falling. So what is the maximum elongation? What is the maximum elongation? What is the maximum length or distance, length, let's say, we can have as an elongation without falling in the object? And tell me, what is the respective equilibrium in that scenario? What is the respective equilibrium of the object in that scenario? What is the respective equilibrium of the object in that scenario? Stable, neutral, or unstable? What is equilibrium? What is the respective equilibrium? Neutral, no? Neutral. Neutral. Now, if we are keeping one object in the neutral equilibrium like this, look at here. If you are keeping only one object in neutral equilibrium like this, one object in neutral equilibrium like this, right? One object in neutral equilibrium like this, then its center of gravity and the acting line of weight should be exactly at the end of the border, no? Then it won't fall. It won't fall, right? So likewise, I'm going to use that idea starting from the object at the top, right? So when there are multiple objects given, starting with the object at the top is easier, right? When there are multiple objects given, starting from the object at the top of the set is easier, right? So let's start from this one. Look at here. Now, if I start from this one, without folding the first one, see, without folding the first one, look at the board, without folding the first one, if I keep the very first book as, right, exactly as 12 centimeters, sorry, 12 mm at 6 centimeters, because say this weight is W, that weight is W. Now, exactly if we keep this 6 centimeters from here, if that is 12, right? Now, this is at neutral equilibrium, no? Now, this is at neutral equilibrium. So, it won't fall. Since there is a neutral equilibrium, it won't fall. Since there is a neutral equilibrium, it won't fall. That's the idea. It won't fall. Now, since it won't fall, now if we think of the equilibrium of the second object, right? Since it won't fall, if we think of the equilibrium of the second object, like this, if we think of the equilibrium of the second object, right? Now the thing is like this. Now the thing is like this. Now there is a force W already acts on the second object by the first object, right? There is a W already acts on the second object by the first object. And other than that, the own weight of second book is also acting from its center of gravity, no? Own weight of second book, right? Own weight of second book also acts from its center of gravity, right? Now, can you see there are two forces acting on the second book? There are two forces acting on the second book, because from the first book also it has a force created on the second book, right? And its own weight is also there. Now, if I think of the second book, right? There are two forces acting, there are two weights acting on the second book, right? Then center of gravity of the second book should be the resultant point where the resultant weight of these two acts, no? Right? Center of gravity of the second book should be, right? Second book in the sense, not only the second book, second and first, because now when I consider this W here, which means I have already considered about the first book, because that's why this W came. Now, if I think of the center of gravity of these two forces, if we think of the center of gravity of these two forces, right? Center of gravity of these two means the point where resultant weight of these two acts, then that should be the resultant weight of these two. Then that connecting point should be, right? Then that connecting point should be the center of gravity of these two. Because center of gravity is the point where the resultant weight acts, right? Now, if the resultant weight of these two, that is 2W, acts somewhere at a point, that particular point should be the center of gravity of these two objects. That's clear? Right. Now, using our theories, if I find this out, now we know if the forces are W and W, the resultant is 2W. Right? So let's say this point is G. Now if there is G, right? If there is G, let's say now this is given, no? B, A, right. If I need to find BG, at once we can find BG now using our theories. See, BG equals, right? Total is 6 centimeters. Total separation is 6 centimeters over resultant 2W times 2W times not connected force W. These two cancels. See, it says 3 centimeters. It says 3 centimeters BG. Then what it says is BG should be 3 centimeters. Right. Now my logic is this. Look at the board. Now my logic is this. Look at the board. Now 2W acts from here. What is 2W? 2W is the resultant weight of both books. Resultant weight of both books acts here. Resultant of both books acts here at G. Right? Then center of gravity of first two books should be here. Right? Now, if I need to keep this whole system in neutral equilibrium, now center of gravity of the whole system is at here, no? Then if the table is like this, if the table is like this, if we keep this on the table like this, if we keep this on the table like this, it won't fall. It won't fall. Why? Because center of gravity of the system is at here, and now if the table is like this, right? Table is like this up to this point, the system is at a neutral equilibrium. So as an individual object, this object itself is in the neutral equilibrium, and as a system, the system also in the neutral equilibrium. Then if we displace this by even a little bit hereafter, this will fall, right? If we displace this just by a little bit, even by a little bit hereafter, this will fall, right? Therefore, this is the neutral equilibrium. And now my question was maximum horizontal distance between C and A. No? Now C is here, C is here. So distance between A and C is 6 centimeters plus 3 centimeters. Right? Final answer 9 centimeters. Right? So this is how this idea is used. And always when you are asked to maximize something, this is a very popular question type we get in center of gravity. Right? When you are asked to maximize something, right, we will be focusing on the neutral equilibrium. And if you are given multiple objects, always start balancing the objects from the topmost one. Start balancing the objects from the topmost one. And each and every object coming downward should be in the neutral equilibrium. Right. Raise your hand if this idea is clear. And you can raise questions if there's anything to know. Okay, take it down if it is clear. Take it down. Now only this diagram is given. Then using this diagram, this is how we organize the question. Right, that is how we organized. right? Right. Write down below in red. Write down below in red. Start. First point. Start considering equilibrium. Start considering equilibrium. Start considering equilibrium. Start considering equilibrium from the topmost object. Start considering equilibrium. Start considering equilibrium from the topmost object. Start considering equilibrium from the topmost object. Second point. Second point. Second point. The minimum condition to be satisfied. The minimum condition to be satisfied. The minimum condition to be satisfied. The minimum condition to be satisfied to keep objects. To keep objects. To keep objects in. To keep objects in equilibrium. To keep objects in equilibrium. To keep objects in equilibrium without falling. Without falling is without falling is neutral equilibrium. Is neutral equilibrium. Is neutral equilibrium. Next point. Center of gravity of. Center of gravity of. Center of gravity of both books. Center of gravity of both books. Center of gravity of both books is now at. Center of gravity of both books is now at. Is now at. Is now at Center of gravity of both books is now at point G. 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 Okay, right. Now, I will give you another question to try by your own. First, tell me whether it is clear about this idea. Is it all clear about the idea? Now, I'm going to give you another question to try by your own. Is it all clear about the idea? Right. Let's move on. Next question. Next question. Write down two books. Write down two books. Two books. Two books of each length. Two books of each length. Two books of each length. 12 centimeters. Two books of each length. 12 centimeters. But different mass. But different masses. But different masses. M and 2M. But different masses. M and 2M. Are kept on a table. Are kept on a horizontal table. Are kept on a horizontal table. Are kept on a horizontal table. As shown. Are kept on a horizontal table 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 as shown. What is the maximum elongation of books? What is the maximum elongation? What is the maximum elongation? What is the maximum elongation of books? What is the maximum elongation of books? That can be gained by the system. Maximum elongation books that can be gained by the system. From the edge of the table. 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 Without falling them. From the edge of the table without falling them. Without falling them. Without falling them. Okay, take it down and try now. Try it. Try it now. Start the question. Right. Any answers? Right. Eight. Let's see. Now, if we balance the first one, right, as before, first one can be at the neutral equilibrium. First one will be at the neutral equilibrium if 6 centimeters. This is kept from 6 centimeters from the first one. Then like this, center of gravity is here, say that is mg, right? Mg, and give me 1 minute. And then, right, and then this will be 6 centimeters if that is at the neutral equilibrium. So this is neutral. Neutral. Now, if you come to the second one, right? So in second one, from its center of gravity, 2 mgx, its weight, 2 mgx. From its center of gravity, it should be 10. Okay. From its center of gravity, 2 mgx, 2 mgx. Now, resultant of these two should be in between, right? So say this resultant is 3 mg, 3 mg. Now, if I need to find the distance to this point, say g, from here, let's assume this as x. So x can be written using our force dividing ratios as total distance. Total is from here to here. Still that is 6. Total is still 6 centimeters over resultant 3 mg, right, into not connected force 2 mg, right, 2 mg. Then mg to mg cancels. X equals 4 centimeters. X equals 4 centimeters. X equals 4 centimeters. Right? X equals 4 centimeters. And if the table is kept, if the table is here exactly like this won't fall. This won't fall. So both at neutral equilibrium. Therefore, maximum elongation. Therefore, maximum elongation is 6 plus x. That is 6 plus x is 6 plus x is 4. 6 plus 4, that is 10 centimeters. 10 centimeters. Right? Yeah, final answer 10 centimeters. Final answer is 10 centimeters. Right. Now, if you compare this with the previous one, the idea we can have is when the object below is heavier, right? When the object below is heavier, the elongation is higher, elongation is greater, right? You can elongate this more, something like that. Okay, take it down, make changes if anything, correct it if anything, make your changes if anything. Take it down. Will you take 2 mg? Yes. This is 2 mg. Right. Same logic as before. Write down below with a red pen. Write down below with a red pen. Whole system is at neutral equilibrium. 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 When books are placed, according to, above distances, when books are placed according to above distances, right. Next one, and this will be the last one from this type. We are discussing today. We'll discuss more questions on the next day with the other types of applications, right? Okay. Next one. Write down 3 bricks of each length, 3 bricks of each length, 24 centimeters, 3 bricks of each length, 24 centimeters, each length 24 centimeters, and different masses, m, 2m and 3m. m, 2m and 3m are kept on a horizontal wall, as shown, What is the maximum elongation? What is the maximum elongation? Point A can have? What is the maximum elongation point A can have? What is the maximum elongation? Point A can have? What is the maximum elongation point A can have? From the edge of the wall. From the edge of the wall. Okay. Take down the diagram and write. Now for this one, all of you should get the same answer. This will be the last question we are discussing from this type. Okay, right? 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 When you answer, I'll start in a minute. Okay, have you got answers? 26. Answer is 26. Okay, that's it. That's it. To balance the first one, to balance the first one. Now I'm going to use the same diagram, right? To balance the first one, we know center of gravity of the first one should be here, right? So let's say that is mg, weight is mg. Then in that case, this should be 12 centimeters, no? If I use the same diagram, right? And weight of the second one is 2 mg, that acts from here. And if the resultant of these two, 3 mg acts from here, first two will be balanced, right? Now in that case, if I find this x, right, it is done. Okay, x can be written as total is 12 over resultant 3 mg into not connected force 2 mg, right? Not connected force 2 mg. Mg to mg cancels. So this is 8 centimeters, no? 8 centimeters. Now 3 mg acts here, and we know 3 mg. This own weight acts from its center of gravity. Its center of gravity here, and if total acts from here, 3 mg plus 2 mg, 3 mg plus 3 mg, 6 mg acts from here. This will be the final and the resultant center of gravity of the system here, right? Then let's assume this as y in that case. So y can be determined as total separation is still 12. Total separation is still 12 over resultant 6 mg times not connected force 3 mg. Right? These two cancels. Right? Then 2, which means 6 centimeters. 6, eh? Right. So therefore, maximum elongation is this 12 plus x plus y. 12 plus x is 8 plus y is 6. Right? Altogether 26 centimeters. Right. I saw this answer. Yes, it's correct. 26 centimeters. It is correct. Good. Now it's clear, right? It is 26 centimeters. Take it down. Make if any changes. Correct if any changes. Right? Okay, let's move on. Okay, write down this as a question. Write down this as a question. Right? Another type from balancing questions. Another type from balancing questions. Okay, write down. Write down. Write down. A cube of a cube. A cube. Sorry, a cuboid, not a cube. A cuboid of a cuboid of a cuboid of given dimensions. A cuboid of given dimensions. A cuboid of given dimensions is placed a cuboid of given dimensions is placed on a rough inclined plane is placed on a rough inclined plane is placed on a rough inclined plane placed on a rough inclined plane as shown is placed on a rough inclined plane as shown. is placed on a rough inclined plane as shown. Rough inclined plane as shown. What's the maximum value of angle? What's the maximum value of angle? Theta. What's the maximum value of angle theta? What's the maximum value of angle theta? What's the maximum value of angle theta? Can be taken by inclined plane. 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 Can be taken by inclined plane without falling the cuboid. 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 Right. Take down the diagram. Right. Listen. The same logic again. The object falls if center of gravity or actin line of weight jumps out from the supporter. If it is outside the supporter, right? Now in this case, the supporter surface is this. In this case, supporter surface is this. This is the supporter, right? Now, if center of gravity is actin line of weight and center of gravity is inside the supporter, it won't fall, right? If it is inside the supporter, it won't fall. Then maximum angle can be obtained as it doesn't fall is when this actin line of weight acts at the edge of the supporter. Same logic, same logic. So its neutral equilibrium should be when this actin line of weight acts at the edge of the supporter. Acts at the edge of the supporter. Now in that case, the diagram will become like this. Right? In that case, the diagram will be like this. At the maximum angle, when weight acts, that weight should exactly act through this point. So we know this is one of the symmetric lines. This is another symmetric line. Right? Now if this is 2A, this is A. This is A. Right? And this side is A over 2. A over 2. Like this. Now in this case, this is a neutral equilibrium. Neutral equilibrium. Actin line of weight is at the edge of the supporter. Actin line of weight is at the edge of the supporter. That's a neutral equilibrium. Right? Now, using the diagram, find where theta is and try to write theta using these values given, using these lengths given, values in the sense lengths given. That's it. Same logic. Right? Okay, any values? Any answers? If this is theta, see, this angle is 90. This is 90 minus theta. This is 90 minus theta. This becomes theta again. So easily we can write tan theta, isn't it? Tan theta equals, this side is A over 2, opposite side A over 2, adjacent side A, right? Then simplify this, tan theta equals A to A cancels, right? A to A cancels, right? Then only half remains. Then theta equals tan inverse half. Tan inverse half. Maximum angle that can be taken is tan inverse half. If the angle is a little bit greater than this actin line is going to go out of the supporter and it falls, and this falls, right? So that is tan inverse half. Tan inverse half. Tan inverse half. Okay, finished? Finished? Any questions? Any questions? Anything to clarify? Anything to clarify? Any questions? Right. So if no any questions, we can wind up. Now with this, we have come to the end of all theory parts we have here in center of gravity, right? We have come to the end of all theory parts we have here in center of gravity, right? So other than these calculation methods, another popular most popular way of coming questions is without giving any length, just the shape is given and some points are given. This MCQ type, we have to guess, you have to predict where the center of gravity is, right? That is another very popular type of questions, right? So next day first we'll be completing all the types of applications of these theories again, right? Now today also with the examples I have covered different types of applications, right? And next day we'll be covering more types of applications on the route, right? And then center of gravity guessings are there, and mass removals are there. I didn't discuss any mass removals today, right? All of them were mass additions, right? Even if I gave you combined objects, all of them were mass additions. There is another type as mass removals. Mass removals we'll discuss, and the last part of here will be center of mass questions, right? Those are the things to be covered next day, right? Those are the things to be covered next day. So after next week, center of gravity will be completed, and after center of gravity, day after next day, we'll be starting friction, as I told you, right? Friction. Okay then. Any other questions? Any other questions before winding up? Anything? Is it all clear about the things we discussed today? Is it all clear about the things we discussed today? Clear? Right. Okay then. So if there's no questions, we can wind up, right? We can wind up. Now we are in the 26th week before the exam, right? Exactly, you got 26 weeks and 5 days here onwards. 26 weeks and today is Tuesday, no? 4 days, not 5 actually. 4 days here onwards, 26 days and 26 weeks and 4 days here onwards, right? So without wasting your time, study hard, right? Work hard, right? So this is a highly a crucial time, right? Highly crucial time, right? That whole your life is going to change, right? And whole life, what you are doing after A levels, based on this, depends on this timeline, this time of your life, right? So make it wisely, use it wisely, and make the maximum out of it. Make the maximum use out of it. Right? Okay. Then, if no any questions, we'll line up. All right then. Then we'll be meeting tomorrow. Meeting next class, not tomorrow. And S2A discussion will be happening on Fridays as usual, and reverse class is on Saturday as usual. Right? So there are more things, more work to do. Right? So we'll be on these things for these coming weeks as well. Right? Okay. And yes. Another practical seminar is also coming up, and another optical instrument seminar is also coming up. There are more things, right? So you can get all updates through the channels. All right then. Then if no questions, we'll wind up. See you in the next class. Right? Good afternoon. Goodbye.